Okay, so as I said a second ago, they're your success criteria. So we are going to start today by having a look at this trig identity. Now, I'm using an example from the exercise book, from the textbook. So if you look at the example on page 461, you'll see it. This is really important. The way I prove a trig identity is definitely different from the way they prove it in the textbook. My proof is the best way to do it. Their way in the textbook is an awful, horrible, terrible way to do it. Okay? Technically, though, at standard level mathematics, the way they do it in the textbook would still be perfectly permissible. So if you can't follow the way I'm doing it, then you certainly, and the way in the exercise book makes more sense to you, then technically you can do it. Let me go through the example first, and then at the end, I'll just have a quick discussion about why I don't like the textbook and why my way is the best and awesome. Is that okay? All right. Is that pumping up the way I'm doing it enough? Okay, so in the textbook, it says that you need to prove that 1 plus tan squared x, so remember, that means that tan x, whatever value tan x is, has been squared. 1 plus tan squared x times the cos of 2x is equal to 1 minus tan squared x. Hi, Izzy. So just as I'm thinking of things, just note that you don't need to have the brackets around the x here. It's just because sine, cos, and tan are so common, they often go without brackets. But can you see how I've got cos 2x here? Because the argument for cos is 2x, you absolutely need brackets there. Because without it, we wouldn't know whether we're talking about cos of 2x or cos of 2 times x. In fact, technically, without the brackets, you'd have cos of 2 times x, if that kind of makes sense. Okay, so the brackets say this is the full argument for cos. Just raise your hand if you're not too sure about that, or ask a question. Goodly doodly. Okay, so this is the solution. It will go over more than one slide, but I'll try and fit it between 11 and 12 there. Okay, so what we have there in that statement, that proof statement, is an equation. And what we know about equations is that equations always have a left-hand side and a right-hand side. And what makes an equation is that the left-hand side is exactly the same as the right-hand side. In other words, if I substitute a value in for x and solve on the left, I'll get a number. And if I substitute that same value for x on the right and solve, I'll get the same number. Otherwise, that equation would not be true. There are inequations where the left-hand side might be less than the right-hand side, or the left-hand side might be bigger or not equal to. So they're all inequations. But for an equation, whatever we have on the left-hand side must be the same as the right-hand side. So the name of the game when proving using trig identities is to take one of the sides. It doesn't matter which side, but you pick the side that you think will be the most fruitful for you. Take one of the sides and manipulate that side until it looks like the right-hand side. Because if I can change the left-hand side, step at a time, until it looks like the right-hand side, then the equation is proved. So that's the long goal there. Now, I love trig identities. I think they're lots of fun to try and nut out. They're basically like puzzles. And in this case, when I present my solution to you, I'm not going to make any wrong turns, but I might point them out. Okay? Over time, you make fewer and fewer wrong turns, but at the start, what you might do is you might start trying to solve this and find that you run into a dead end. And when you do, you might need to backtrack and try a different method. Okay, I'm getting a couple of frowns there as if to say, what are you talking about? So let's just go on with it. So the first part of the solution is to choose a side. I'm going to choose the left-hand side. And the left-hand side is 1 plus tan squared x. I won't use the brackets this time, so you can sort of see that. times cos 2x, like so. That's the left-hand side. And so I'm leaving the right-hand side alone. And now I need to try and do things that will enable me to get to the right-hand side. Now, at the end of the day, you have to try something. So we've only got limited identities. I'm going to flick back to the other pages just for a second, just to remind you of those other trig identities. Okay, so we've got those ones. Do they look familiar? Hope so. And then yesterday, or last lesson, sorry, we looked at that one, the three forms of the cosine double angle identity. And then there's the sine double identity. Why have I got identity twice there? I meant to say double angle identity, didn't I? So weird. Double identity. Double angle identity. There we go. Okay, so they're the ones we're going to use. Now, you can have those as a list next to you on your page as you're trying to figure it out. Now, you can use some intelligence to try and figure out, but even the best of intelligence may still end up giving you a wrong pathway. But what I see is that but using a little bit of intelligence, it might not get, well, it will, but it might not get you anywhere when you try this. But I can see that I've got a 1 minus tan squared x. I clearly don't have any 2x's in my right-hand side. So I'm going to try and get rid of that 2x because I think that's the thing that I need to get out of, okay? Cos 2x. Okay, so I know that cos 2x could be cos squared x minus sine squared x, or 1 minus sine squared x, or 1 minus 2 sine squared x, or 2 cos squared x minus 1. So I can choose one of those forms, and I'm going to replace cos 2x with one of those forms and see where it takes me. Okay, now I'm thinking a little bit further ahead. Okay, so you might just, at this stage of your proving, you might think, well, I'll try cos squared x minus sine squared x, something like that. You might just try something, and it will get you there, or it won't get you there, or it might make it more complicated or not. Now, I'm thinking a few steps ahead and know that I reckon I can do something with the fact that tan squared x is sine over cos. So I'm thinking a little bit further ahead. And so I'm going to settle on replacing cos 2x with 2 cos squared x minus 1. Okay, so I've replaced cos 2x in that expression with 2 cos squared x minus 1. That's the double identity. If you want to be really fancy schmancy, you can put the if you're doing HL, they would make you put the reasoning on the right-hand side here, but I won't force that on you. But that's the way you really do it. You put your explanations on the right-hand side to say what you're doing. Okay, so that's as far as I've got. What I'm going to do now is I'm going to expand those brackets. So whether you use the box method or the chicken beak method or the cross method, whatever else it is, or the FOIL method, I'm going to go 1 times 2 cos squared x is equal to 2 cos squared x. 1 times minus 1 is minus 1. Tan squared x times 2 cos squared x is positive 2 tan squared x cos squared x. And tan squared x times minus 1 is minus tan squared x. Now, I get to this point, and I can see that I've got a tan squared x here, a minus tan squared x, which is what I've got up here. And so my thinking is, if I can sort of make all of this somehow equal 1, I will have it equal to the right-hand side, and it will be proven. Okay, so it doesn't look like it right now, but I can see that this is getting closer to the solution. So I won't touch that, which means I need to try and touch all this kind of stuff. Now I've got a 2 cos squared x here. I've got a 2 tan squared cos squared x here as well. So what I'm going to do is I'm going to replace the tan squared x with sine squared x over cos squared x times cos squared x minus tan squared x. And I did that simply because I could see that those causes will cancel out then. Okay, so I'm thinking, so if your fraction works a bit weak, then that's not going to be immediately obvious to you. So I'm thinking that's going to get me somewhere. All right, so I will cross out the cos squared x on the bottom with the cos squared x on top. And that gets me, so I'm just going to leave it zoomed out now. And that gets me, oops, left-hand side equals 2 cos squared x minus 1 plus 2 sine squared x minus tan squared x. Now this looks like a horrible mess, but I can see the glimpse of a solution from this point on. Because what I see here, I know it's not next to each other, but can you see that there's a 2 cos squared x here and a 2 sine squared x here? So I know that cos squared plus sine squared is equal to 1. It's just that I've got this 2 outside each expression here. But that means it's factorizable. So the next line, I'm just going to factorize the 2 and leave myself with cos squared x plus sine squared x. This is exciting because I know that's going to get rid of those coses and sines, because we know that cos squared plus sine squared equals 1. Minus 1 minus tan squared x. Okay, so cos squared plus sine squared equals 1. And so I'm left with 2 minus 1 minus tan squared x. And 2 minus 1 is 1. So I'm left with 1 minus tan squared x. That is equal to the right-hand side. And if you want to be fancy schmancy, quote erat demonstratum, thus it is shown, thus it is demonstrated. So I have proven that I can take the left-hand side, and by manipulating it, by using the identities which are always true, to replace parts of my left-hand side with other things which are equivalent, I can eventually get to the right-hand side. And because I can get to the right-hand side, it must be that the original equation is true. What do you think? Is that okay? Now, what you didn't see there, I mean, I didn't make any mistakes when I worked it out on paper. Simply just practice, because I've done heaps of them before. Okay, so I've got a better eye for which ones will get me to the right solution. The truth is, there are probably 3 or 4 or 5 or 6 different pathways that will get you left-hand side equals right-hand side. Maybe there's a pathway there that will get you there shorter, in a shorter number of steps than I've got there. I don't know, but that's the way I decided to do it, and it worked. Sometimes you will use identities which don't get you anywhere, because you didn't see that it would have this kind of effect. And so you're going somewhere and then you sort of hit a dead end. I can't get to the right-hand side from here. And that's when you have to backtrack and try different identities to try and see if you can solve it. So it is a little bit of a putting a puzzle together kind of thing. You know, like a Rubik's Cube, really, solving a Rubik's Cube, where you might do a whole bunch of different combinations and find that you've actually make it more scrambled instead of less. Then you might need to, if only you could, undo the moves you did on a Rubik's Cube. So that's it for that proof that I've got on the board there. I'm just going to stop and ask for any questions before I just explain to you why I don't like what's in the book. No, that means you're either just letting it sink in or you were pretty right with that. If you have a look in the textbook, if you've got access to the textbook or looking on with someone would be good. We're looking at example 10 on page 461, the one that I just did. If you have a look, what's the difference between the way I solved it and the way the textbook solved it? Having a quick glance down apart from the fact that maybe it's a bit shorter, maybe. Bit louder, Izzy? Yeah. Everyone see that? In order to prove it, they changed both sides. Now, there's a certain lack of elegance of doing that, because what you're doing is you're fundamentally changing the equation from what it was originally to to a new equation. Now, technically, there's nothing wrong with it, because as it says at the conclusion at the bottom here, if you can sort of get both sides of the equation down to something which you know to be true, i.e. a trig identity, or something like 1 equals 1, if you can reduce both sides down so that you know that the left-hand side equals the right-hand side, technically you have shown that the original equation must have been true to start with, because the only way you can end with a correct equation is by starting with the correct equation, assuming you haven't made any mistakes all the way through. But in terms of solution solving, the one that I've done on the screen is a better way of solving your trig identity problems, because it leaves one of the sides untouched. So all you're doing is you're directly proving that the left-hand side can be made to be the same as the right-hand side. So there's a lot more elegance to the solution. The communication in terms of what you're doing is a lot clearer. And thus it would be considered, I mean, all the way through my university degree, if I were proving stuff to be true, it would always be done in that model for that reason. The one slight practical problem with doing it the way in the textbook says, just on a practical level, is that sometimes, because you're manipulating both sides of the equation, you can sometimes make double mistakes, double errors kind of thing, because you're manipulating both sides at the same time. And there is that sort of potential for errors to creep in because you're manipulating both at the same time. And that's when things can get a little bit hairy. You might prove it in the wrong way. In other words, you might get the right result because you made a couple of mistakes which cancelled each other out, or you might not be able to prove it because you've made a mistake left and right with your balancing the equation work. So there is a little bit of that as well, but that's not really the main reason why I'd say don't do it the way that the example does. Having said that, though, you can see that my solution here does require a few more steps. I think it's clear, but it does require a few more steps as a result. If I was doing this for real, I mean, even if I look at my rough notes that I wrote today, I didn't use quite as many steps as this. I did more steps than necessary just to spell it out, really, for you guys and for your notes. But yeah, I reckon it's slightly longer, but I think it's still a better way of doing it. If you can handle that, that's the way I'd like you to do it. If you feel like you've looked through the example 10, you think, actually, that makes more sense to me, I'm not going to, object too strongly. But if you can do it that way, I think that's the better way. Okay, any questions? All right, so I'm just going to give you the next 20 minutes, I think, to do some practice. So we are looking at exercise 13F. And I don't have the page number there, but it must be around about 461, 462, something like that. And I think if you can do question 1 to 4, just the right-hand side, and then question 5, 6, and 7, I know that's more than you can do in 20 minutes, but if that's what you use as your framework there, even if you do at least one from question 1 to 4, that would be a bare minimum. But if not, the right-hand side. And then question 5 is when you start doing these trig identities that I've just gone through. So questions 1 to 4 find the value of x, solve the equation. And then questions 5, 6. Question 5 is all those trig identities, and 6 and 7, I think from memory, are exam style questions. Okay, and I'll come around and help you.